These are the notes for AP Calculus on the topic of the derivative rules. So on this first page here, put down the constant rule, derivative constant 0, the power rule we use all the time, bring down the exponent, reduce it by 1. The constant multiple rule, where the constant in front of the coefficient just stays there when you take the derivative. Sum and difference rules, just saying you can, when terms are added or subtracted, you can take the derivative separately. Product rule, where you follow the pattern, the derivative of the first one times the second one as it is, plus the first one as it is times the derivative of the second. Quotient rule, we do the same pattern, except it's a minus instead of a plus, and then divided by the denominator squared. The chain rule, where you take the derivative of the outside times the derivative of the inside. And the double chain rule, where you take the derivative of the outermost function times the derivative of the next one inside times the derivative of the next one inside. So let's see how these work together on some different example problems. It says find the derivative of each function, write your answer without negative or fractional exponents. So overall here, notice we've got e to the x cubed times the natural log of cosine x, so that's a product rule overall there. Easy. And now let's find h prime of x. And notice when you take the derivative of the first one, it also is going to involve the chain rule, because we got x cubed up there. So the e part, remember, stays the same. So it'd be e to the x cubed. But using the chain rule, you have to multiply by the derivative of the function inside. So the derivative of x cubed is 3x squared. So that's the derivative of the first one. Then times the second one as it is, natural log absolute value of cosine x, plus product rule. The first one as it is, e to the x cubed, times the derivative of the second one. Notice again, we've got another chain rule here, because we've got cosine x inside natural log. And then remember the derivative of natural log of x is normally just 1 over x. Here, it's 1 over cosine x, whatever's inside of it. And then times the derivative inside, the derivative of cosine x starts with a c, so the derivative is negative some. And there's just a little simplifying we can do here. Notice both of these have a e to the x cubed, so you could factor that out as a DCF first, a little simpler. And what we'll be left with is 3x squared, natural log absolute value of cosine x. And then here, notice this negative you can bring out in front, so it becomes minus to the plus there. And then e to, we already factored out the e to the x cubed, so then we've got sine over cosine, or you could simplify that to just be tangent over cosine. So that would be our derivative for h prime of x. Let's take a look at this one here. So here we've got sine of 4x divided by 2x minus 4, 2x minus 5 to the fourth. So overall, this is a quotient rule problem. Notice again within that we've got a couple chain rules, because 4x, you can even put parentheses if it helps you, is inside of sine, and we've got 2x minus 5 is inside this power of 4. So we find the derivative here, it's y equals, remember we'd write the derivative as dy dx. On a similar pattern to the plus, where you take the derivative of the numerator first, and that involves the chain rule, so the derivative of sine is cosine. And the function size stays the same, so it'd be cosine 4x, but then times the derivative inside, derivative of 4x is 4, times the denominator as it is, 3x minus 5 to the fourth. This time it's minus, so instead of plus, because it's the quotient rule. The numerator as it is, sine of 4x. And then using the chain power rule here, b times the derivative of the second one using the power rule first, would be 4 2x minus 5 cubed. But then using the chain rule times the derivative inside, derivative of 2x minus 5 is just 2. And then don't forget on the quotient, it's all divided by the denominator squared. 2x minus 5 fourth squared. All right, then to simplify, notice again we have a GCF we can factor out of the numerator. They both have a 4, and they both have a 2x minus 5 cubed. So we can pull both of those out. GCF. And then let's see what we have left when we do that. So we still have the cosine of 4x and a 2x minus 5. You can put either one first. I'll just put the 2x minus 5 first. So what's to the fourth? We factored out 3 of them. Minus, here we took out the 4 and the 2x minus 5 cubed, so we just still have this 2 chain row in light blue here, and we still have sine of 4x. All divided by, if you multiply the exponents here, it gives you 8, so 2x minus 5 is 8. And then you can reduce a little bit. You both have your 2x minus 5 cubed. 3 of those cancel out, leaving you with 5 there. Subtracting the exponents. So our final answer here is the derivative 4 times 2x minus 5 times cosine of 4x. Minus 2 sine of 4x. All divided by 2x minus 5 to the fifth. Alright, let's take a look at the next one here. So in this one with the radical form, it tends to be a little easier if you first rewrite it. So let's go ahead and do that first. So I'll rewrite this as f of x equals, the cube root is the same as raising to the 1/3 power. And then inside that we've got natural log. And inside natural log we've got square. So this one is an example of a double chain. We've got two functions inside. I'm going to take it through. So this is still just the original function. Now let's go ahead and find the derivative. F prime of x. So start on the outside and work your way. So using the power on the outside would be 1/3. The function inside stays the same, natural log x squared minus 5x plus 1 to the negative 2/3. Subtract 1 from x, subtract 3/3. That's the derivative outermost. Then the derivative natural log. Normally it's 1 over x again. Here it's going to be 1 over x squared minus 5x plus 1. And then times the innermost function, the derivative one in green here is 2x minus 1. And then you can just simplify that a little bit. So let's see, the only thing we're going to have on the numerator here, because this is a negative exponent here, is this 2x minus 5. And on the denominator, let's see what we've got. We've got this 3 here from the 1 on the denominator. And we've got this x squared minus 5 to x plus 1. And then in radical form, this would be the cube root squared of natural log x squared minus 5x. You can leave the 2x minus 5 in parentheses, but you don't have to put it there. That's all. Let's take a look at the next one here. So we got y equals arc sine of e to the 5x plus x. So the outer function then is our inner function, and then we've got another double channel, just slightly different, 5x right there. Then we take the derivative of y dx equals, well, let's start on the outside. The derivative of arc sine, remember, is 1 over the square root of 1 minus, normally the x squared, but it's whatever is inside of arc sine, so it'd be e to the 5x plus x squared. And then times the derivative inside, and the derivative inside, notice, the derivative e to x is just e to x, but you have to multiply by 5, so 5 e to 5x. And not too much to simplify here. Rather than dy dx, 5 e to the 5x on the red. Oops, I forgot something important there. I thought that was a constant. I forgot about the derivative of plus x is plus 1. Yep. So that's what we have on the numerator, 5 e to the 5x plus 1 divided by, you could square that out, but it doesn't really make it much simpler there, so I'm just going to leave it square root of 1 minus e to the 5x plus x squared. Those are just basic derivative problems. Hopefully that refreshes your memory the rules, formulas there. Let's take a look at some ones that are a little different out of. Oops, too far. Okay. So this one, they tell you f prime of x right here, and they give you g of x, and they're asked to find, well, what's g prime of 3? So, it may not be obvious how it's all going to fit together at this point, but I know we need g prime of 3. Before we can find g prime of 3, I need g prime of x, so let's figure that out first. G prime of x equals, well, notice here's a chain rule one, because f is a function on the outside, x squared minus 4 is the chain rule. So you would first consider the outside. It's just a general function f, so you'd have to write it as f prime. We would do for g prime, the function that x squared minus 4 stays the same. And then using the chain rule times the derivative inside, so times. And then we're asked to find g prime of 3. So you can substitute 3 in there, because that's what we're trying to find, right? 3. So it'd be f prime 3 squared 4 times for the x's. So g prime of 3 equals, well, we can pull the 6 out front, times 3, and then we get f prime of 9 minus 4 is 5. So that's g prime of 3. If we weren't given f prime here, that's as far as we could go. However, now we can see what we actually need. We need f prime of 5. And notice this is already f prime, so we don't even have to take the derivative of it. It already is a derivative. So then you would just substitute 5 into that. Get 5 minus 3 squared. That's 5 squared minus 1 over 4. Well, 5 minus 3 is 2, squared is 4. 5 squared is 25 minus 1, 24. See the 4 is reduced further. So f prime of 5 is 24. And we can substitute that in right here. 3 is 6 24. 3 times 20 is 120. 6 times 24, 120 and 24 gives you 140. So a few more that are a little different. Here we're given, let's say f be a differential function. F of 0 is 2, f prime of 0 is negative 3. Again, you might not know when we need those yet. But it says h is sine of ax times f of x. Write the equation of the tangent line tangent to h, in terms of a. That means a is going to be our answer. All right, so point tangent line, you need two things: point of tangent and the slope. And it says we want the tangent line here. I think I forgot to add here. H should say the x coordinate at x equals 0. Sorry about that. Since these are both at 0, it makes sense that that's where we're finding the tangent line, but it should say that. So then we can find h of 0. The sine, a times 0 is just 0, times f of 0. Sine of 0 is just 0. That wipes everything out. F of 0 is 2. So we still get 0. So plugged in 0, we got 0. So 0, 0 is our point of tangent. Just right through the origin. And then to get the slope of the tangent line, yeah, that's where the derivative comes into play. We have to find h prime of x. And notice again, we've got to use sine of ax times f of x as the product rule. So remember the pattern, take the derivative of this one. Derivative sine ax, cosine ax. Remember, a is a constant, so using the chain rule on that, the derivative of a x is just a, just like 5x would be 5. And then the pattern, the product rule, then it says the second one as it is, plus the first one as it is, sine of ax, times the derivative of the second one, the derivative of f of x, you'd write then this is our slope for any point in the graph. We want it specifically at times at x equals 0 at our point of tangent. So well, 0 times a is just 0, so cosine of 0 times a times f of 0 sine of 0 times f prime. Set the value like this. So the cosine of 0 is 1 times a. F of 0, they give us right up here 2. Sine of 0 is 0. So you don't even need f prime of 0, although it does tell us that. It's negative. It's not going to matter though because you put the 0 in. That wipes that out. So all we're left is 1 times a times 2, so 2a. So we can write our tangent line, 1 minus 0 equals 2a times. But the zeros there means that simplifies to just y equals 2x. These equations. All right, let's take a look at a couple more here. On this one, it says given the function p is given by this, where k is a constant. If p prime of 1 equals 4, find the value of k. So if we want to utilize this point, f p prime of 1 is 4, that's a point on the derivative, we're going to need to know the derivative of this. So p prime of x, or added, so you can leave the derivative separately. So x to the k, remember k is a constant, so this could be to the fifth. You just use the power rule, so it'd be k x, and remember the exponent reduces by 1, so it's k minus 1. Plus, here we've got of sine, cosine, and then use the chain rule times the function side by x, the derivative for x. And then we've got this point, the derivative at 1 has to equal 4. So we can plug that in. Plus cosine of, and you plug in 1 for x, that's cosine of 5. So you plug in 1, and notice we know that p prime of 1 equals 4. So here you have to use a special property. 1 to any power is always 1. So that's just 1 times k. So that's 1k. And then cosine of pi is negative 1. So actually, minus pi. And add over the pi, we end up getting k is that's what it asked for, find the value of k. So go one more a little different. This one we're going to use the graphing calculator on. So it says let f of x and g of x be functions given by these two equations. On what interval or intervals is the rate of change? Remember, rate of change, just another word for the derivative or slope. Let's say at what intervals is the derivative of f of x greater than the derivative of g of x? So to figure that out, we actually need to know the derivative. Okay? So let's start with f of x. F of x. Chain rule here. The e part stays the same, remember? So say e to the 0.8x. Using the chain rule, though, that can get multiplied by the derivative of 0.8x, which is 0.8. F of x greater than the rate of change of g of x. So g prime of x would be, the power rule just looks weird with the decimal there, so you bring down the power, 4.4, reduce the power by 1. All right, I want to see when is this one greater than this one. So we've got to enter these both in our calculator. I'll do this on the 84, similar process for the fire here. Just go 0.8 e to the 0.8x, and then for g prime of x, enter that in, 4.4 x raised, let's put in parentheses to make sure it does the whole x to the 3.4. I want to know when does this one, and does y1 greater than y2? So we can look at the graph here. I've just got the standard Windows figure. So there's the graph of E, and there's the graph of the other one. So you can see there is one point of intersection we can see here. Now here's where it's important to remember that this E, this exponential one, remember we said is larger than this one eventually. But right now in our graph it doesn't look like that, right? Because we've got E to the x is here, and the x to the 3.4 is actually above it. We know that eventually this E has to pass it up though. So we'll make our window size a little larger here. So let's make x maximum, let's try 15 instead of 10, and the y max, let's try 100. So one place they cross, still the E that hasn't passed it up yet. So let's try making our window size even larger. Let's add another 0. See if that's enough. Still not. So we know they're going to intersect at some point in either. So let's try adding another 0. Just kind of playing around until we can find where they intersect. But we know eventually they have to, because E to the 0.8x eventually has to get larger. Getting closer. All right. Let's try this. Not quite out of 0. Let's change it from 10,000 to 50,000. See what they cross. There, we finally see it right there. Okay. So if we draw our number line here, we found 2 points of intersection, which we'll find using our calculator. And if we look back at the graph here, you can see in this middle section, this is where e to the x is less than the g to the x graph, right? And then over here, when this dips down below, remember if you change your window size, see that let's make the y min negative. Oops. See, this one's below the x-axis, and then it eventually crosses this one, where this one is never negative, remember. So they cross here and here. So let's find those 2 points of intersection. And remember on this guy, we do a second calc. Number 5, intersect. First curve, there it is, y1, just hit enter. Second curve, y2, enter. Guess, I'm going to guess this first one's around 0 here. Let's see what the 0 enter. Or you can move your left and right arrows on the cursor. The sign changed there, let's see. Try that again. I think let's try 10,000. Second calc. Intersect. Just gonna regraph it so we can see it a little better. There we do cross there. So I think first curve, second curve, somewhere over here. There it is. So the 0.717. What you need to do on the AP test. And now let's find our other point of intersection. Again, second calc. 5 intersect. First curve y1, second curve y2, enter, and then yes. Use the right arrow or type it in. We want to find this point of intersection here. So that's 13.047. And notice by looking at the calculator here, we can see this is the section where e to the point x is actually less than it. We're looking for where it's greater than it. So this is g prime of x, and then over here it surpasses it, f prime of x is greater than g of x. Because g prime becomes negative. And those are the intervals we're looking for. So f prime is greater, not less than g of x. So in interval notation, we would write that negative infinity to 0.717 u 13.047. Just that middle section works, doesn't work. And that concludes the notes for AP Calculus on the topic of derivative rules.